Hello, in this video we're going to be performing a von Neumann stability analysis to show that there are no constraints when using the Crank Nicolson method on the space increment and the time interval. So on this board is work that we did in the previous video to write out the code for the Crank Nicolson method of a thermal profile of a bar. And so we'll be using some of this information to perform the stability analysis, mainly this equation here, which is what we derived in the previous video. And so to begin, just a reminder, we also did this in a previous video, but temperature is defined as e to the I k x times e to the negative alpha k t. And so using the definitions that we did here, where we discretize the space increments and the time increments, it is e to the I k j delta x, and then e to the negative alpha k n delta t. So the counters that we use for position is j, and the counter that we use for time is n. And so now, when we look at, let's say, the temperature at position j for a certain time, let's just say n, that is going to be e to the I k j delta x times e to the negative alpha k n delta t. And so if we look at the next position, so j plus 1 at n, we would have e to the I k j plus 1 delta x and e to the negative alpha k n delta t, because the time's the same. And then similarly, if we were to look at the previous position, we'd have j minus 1 at time n equals e to the I k j minus 1 delta x, and then e to the negative alpha k n delta t. And so a more in-depth explanation of why this is the case, we also did this in a previous video, but looking at this, we can see that this differences between the temperature at position j and then at the next position at the previous position is just e to the negative, or e to the I k delta x. So if we were to distribute out the I k delta x to the j plus 1, everything else is the same other than this value times tj. And then for the previous position, j minus 1, it's the same, except it's negative I because it's a minus 1 instead of a plus 1, k delta x tj, and then this is at n and at n. And so now if we use this information and we plug it into this equation here, we have negative u. Okay, so we can first, let's distribute out tj. And then so first is we have the negative u, and then it's j plus 1, so we have e to the I k delta x, and then we have plus 1 plus 2u, and then it's j, so we already distributed tj, so we don't need to put anything, and then it's minus u, and then this is j minus 1, so we'll be using this one, so e to the negative I k delta x, tj we already distributed out, tjn technically. And then moving on to the right hand side of the equation, we have u, it's tj plus 1, so we'll be using this top one again, so e to the, well, first we need to distribute out a tjn, but this one is actually tj, over here on the left side, I guess I should have clarified, since we're doing Crank Nicolson, it's two different time interval, or two different times, it's the averages of the two, which is what we explained in the previous video, but, so this is actually n plus 1, not n. And then, but this remains the same, it's negative u e to the negative I. So over here it's different because it's TJN, and then the rest of it is the same except it's the positive, so U for TJ plus 1, so we'll have U e to the I k delta x, and then plus we have 1 minus 2U. It's TJ, so we don't need to add anything. And then we have U TJ minus 1, so we have plus U, and then it's minus 1, so we'll be using this one. So we have negative IK delta X. So now what we can do is we can begin to simplify it. And so when we simplify it, we can divide this onto the other, or divide this side by this, so we'll have TJ at n plus 1 is equal to, we'll have the TJN, and so we have this top equation here, U e to the negative IK delta X plus 1 minus 2U plus UE to the negative IK delta X divided by negative UE to the IK delta X plus 1 plus 2U plus UE to the negative IK delta X. And so what we can actually use is something called Euler's formula, which basically is just that e to the x plus e to the negative x is going to equal cosine, 2 cosine of x. And so we can use that to simplify this here. And so we have TJN, and then we have the 1 minus 2u will stay the same. And then we'll have plus 2u, and then cosine, so the x is just what's in the exponent, so we'll have IK delta x. This should also be positive, not negative. That's my mistake. And then in the denominator, we'll have 1 plus 2u plus 2u cosine IK delta x. And so we have this one that gets distributed out. So we have TJN 1 plus, so we'll have 1 minus 2u cosine IK delta x, and then we'll have 1 plus 2u cosine this would be 2 cosine IK delta x minus 1. This would be 2u cosine IK delta x plus 1. And so what we can do is we can make these look the same by negating the numerator. And so what we would have is we would have TJN 1 minus 2 cosine IK delta x plus 1 divided by plus 1 divided by 1 plus 2u, so I forgot the u in the numerator, 2u cosine IK delta x plus 1. And so basically, since these two are the same, we can just say that this term is w, so we have TJN of 1 minus w and 1 plus w, and it looks really clean. And so if we were to look at it, we have the u value, which over here we define as alpha times time increment divided by 2 times the space increment squared, so it can never be negative, it will always be positive. So u will always be greater than 0. And then the cosine will always be less than 0. So basically w will also always be, or cosine will always be less than 1. And so w will always be less than 1. Or cosine, no, I was right. Cosine will always be less than 0. So w will always be less than 0. And so, okay, so now I see why I was a little confused. I was right when I said that cosine will always be less than 1 when I changed it earlier. So when I changed it and then changed it back and said I was right, I was actually wrong. So cosine will always be less than 1. And then another thing that causes my confusion is when I distributed it, I wrote it out a little quick and made a mistake here. So when I distribute out the 2u, it's going to leave me with cosine ikx minus 1 here, but then here it's going to leave me with 1 minus the cosine ik delta x, and then so when I negated it here, I would change these values to 2u, so 2u, and then this would become 1 minus cosine ik delta x, and this becomes 1 minus cosine ik delta x. And so it's the same, it produces the same thing down here where it's 1 minus w, 1 plus w, but when we go into our explanation it makes a little more sense because 2u is always going to be greater than 0 because u is always going to be positive, and then cosine is always going to be less than 1, and so w will always be, because if we look 1 minus a negative number is going to be a positive number. So 1 minus anything, anything greater than 1 would cause it to be a negative, but since cosine is always going to be less than 1, it's going to basically be 1 minus a number less than 1, which is always going to be positive as well. So that means that w is always going to be greater than 0, greater or equal to 0. And so 1 minus, if we just play out a few situations here, 1 minus a number that's greater than 0, let's say it's 0.5. So if we did 0.5, we would have 0.5 over 3.5, and so that number is going to be less than 1. And then if we had a number that was significantly greater than 0, like, and greater than 1, so let's say we had 2, we would have negative 1 over 3. And so basically what this means is, which is also less than 1. So this value is never going to reach infinity. It's always going to be less than or equal to 1. And so because of that, and because it's never going to reach infinity, there is no constraints. There's not going to be instability, like if we were using explicit differencing. So that's why this stability analysis shows that there's no constraints on the time step and on the space increments because there's no constraints on the u value.